Welcome everyone. I'm excited to kick off our journey into programming with this first lecture. Getting started in C today, we'll explore the fundamentals of C programming language, a powerful and versatile tool for software development. We'll cover the basics, set up your environment, and get you ready to start coding. So, let's dive in and discover what C has to offer. Welcome to Slide 2. Today, we'll start with an introduction to C, which is a fundamental programming language used widely in many applications. We'll also go over the tools we'll be using throughout this course, so you know what to expect. Next, we'll look at the structure of a program file, which helps us organize our code effectively. Then, we'll discuss variables. These are essential for storing data that your program can manipulate. We'll also cover how to read input from the screen and print output to the screen, making our programs interactive. Additionally, we'll explore decision-making using the if statement, so your programs can make choices based on different conditions. Our overall objective is to build a solid foundation in C programming, enabling you to write simple yet powerful programs. Throughout this journey, we'll connect each of these concepts to see how they fit together to form a complete programming process. Created in 1972, C was developed specifically to write operating systems, most notably Unix. It was created by Dennis Ritchie at Bell Labs. Building upon the earlier language, one of the key strengths of C is its portability, meaning it can be adapted to different hardware platforms with careful design, especially if you follow best practices like those outlined in Plodger's The Standard C Library book. This portability has made C incredibly versatile. It was built with a focus on performance and efficient memory management, which is why it's widely used in operating systems, embedded systems, real-time applications, and communication systems. When we talk about C's orientation, it's really about giving programmers a powerful tool to control hardware directly, enabling the development of systems that need to be fast and resource-efficient. Overall, C's design philosophy has had a profound impact on software development, setting the foundation for many other languages and systems. Alright, so on this slide, we're looking at the timeline of the C language standards. In 1989, both ANSI and ISO came together to define the first standard, which is simply called Standard C. This was a huge step forward, because it helped create a consistent foundation for C programming across different platforms and compilers. Then, about 10 years later, in 1999, we saw the release of C99. This version introduced several important features, like new data types and better support for modern programming practices, making C more powerful and easier to use. Fast forward to 2011, we got C11, which aimed to improve aspects like multi-threading and safety. Now, I want to highlight an important point here. When you look up information about C on various websites, you might come across conflicting details. And that's often because of different standards or revisions that have been adopted over time. So, keep in mind that understanding the evolution of these standards helps clarify why some features or behaviors might differ depending on the compiler or environment you're working with. This historical context is key to grasping how C has developed and why standardization matters so much in programming. In 1979, Bjarne Stroustrup developed C++ at Bell Labs, and this was a major step forward in object orientation, allowing programmers to create more modular and reusable code. Then, in 1991, Sun introduced Java, which built on some of these ideas but added new features to make programming even more portable and efficient. One of Java's key innovations is its ability to compile code into Java bytecode, which runs on a virtual machine. This means you can write your code once and run it anywhere that has a JVM, what they call write once, run anywhere. This cross-platform capability was a game changer. Java also includes a memory manager with garbage collection, so developers don't have to manually handle memory management, reducing bugs and making programs more stable. Interestingly, many JVM implementations are written in C and C++, which highlights how versatile and performance-oriented Java's ecosystem has become. As we look at later languages, these innovations set the stage for a lot of the modern, portable, and managed language features we see today. All right, let's break down what's happening here. This slide shows us a simple C program, which makes input and output available to us. The key idea is that open and close braces are used to mark the beginning and end of certain statements, specifically the header and the main function. You'll notice the line with hash include stdio h. This is important because it allows us to access standard input and output functions, like printf. Without it, we wouldn't be able to display anything on the screen. Moving to the main function, which is defined as int main void. This is the entry point of any C program. When we run the program, execution starts here. Inside main, we have a printf statement. Printf, this is my first C program, \n. This line tells the program to display that message on the screen. The \n at the end simply moves the cursor to the next line after printing. Finally, there's return, 0, which indicates that the program has finished successfully. Overall, this slide introduces us to the very basics of writing a C program, using headers, defining the main function, printing output, and ending the program properly. It's a foundational step toward understanding how C programs operate. All right, on this slide, we're looking at the basic structure of a simple C program. It ends the line with the line ends the line, which signifies that each command or statement in C concludes with a semicolon. Then we have ends the program, meaning once the program reaches the end, it stops executing. The next part, prints the message, highlights what the program actually does, displays something on the screen. Specifically, the message, "This is my first C program," is what will appear. The line printf, "This is my first C program," \n, is the command that prints that message. Notice how it uses the print function, which is standard for output in C. The \n at the end adds a new line after the message, making sure the output looks clean. Finally, there's return, 0, which indicates that the program has finished successfully. Returning 0 is a signal to the operating system that everything went smoothly. Overall, this slide introduces us to the fundamental parts of a C program: ending lines, ending the program, printing messages, and returning control. These are the building blocks we'll use as we learn more about coding in C. Now, let's take a closer look at this table comparing C and Java for a simple Hello World program. As you can see, the structure of the programs is quite different, and this highlights some of the key distinctions between the two languages. In C, we start with an include statement, which tells the compiler to include the standard input-output library. Then, we define our main function with a specific signature, and inside it, we use printf to display our message. Notice the use of the return 0 statement to indicate successful execution. Switching to Java, the program begins with a class declaration. Inside that class, we have the main method, which is the entry point of a Java application. Instead of printf, we use system, out, println to output the message. One of the main differences here is the structure. Java is object-oriented, so everything is wrapped inside a class, while C is procedural. This table helps us see how the syntax and organization differ, but both serve the purpose of writing a simple program that outputs hello. By understanding these differences, we get a clearer picture of how each language approaches programming, which is essential as we explore their unique features and use cases in the broader context of software development. Let's walk through the key phases involved in turning a C program into a running application. First, we have the editor, where the programmer writes the code. Once the code is ready, we move on to compiling using GCC. During this process, the preprocessor expands macros and includes headers, essentially preparing the code. Then, the compiler translates each file into machine code, creating object files. After that, the linker comes into play, combining these object files and linking in any necessary libraries to produce a single executable program. When it's time to run the program, the loader loads this executable into memory, setting everything up so it can run. Finally, the CPU executes the program instructions, allowing the computer to perform the tasks we've programmed it to do. Understanding these phases helps us see the entire journey of a C program, from writing code to executing it on the machine. Each step is essential in transforming human-readable code into machine-executable instructions. Now, on this slide, we see the copyright information, which is Copyright Pearson, Inc., 2013, and it states that all rights are reserved. This is a standard reminder that the content we're discussing is protected by copyright law, meaning it cannot be reproduced or shared without permission. It's important to recognize that all the material in this presentation has been created and owned by Pearson, and the rights are reserved to them. This ties back to our overall theme of understanding intellectual property rights and respecting creators' work. So, whenever you're using or referencing material, always keep in mind the importance of proper attribution and legal considerations. Now, moving on to slide 11, I want to highlight that all the content we're discussing is Copyright Pearson, Inc., 2013, and it's important to remember that all rights are reserved. This means that the material is protected by copyright law, and any use or reproduction without permission could lead to legal issues. Throughout this presentation, we're emphasizing the value of respecting intellectual property, which ties back to our broader theme of ethical practices in education and information sharing. Recognizing copyright protections helps us understand the importance of creating original work and properly attributing sources. So keep in mind, respecting these rights is not just about legal compliance. It's about fostering integrity and trust in our professional and personal interactions with information. Now let's talk about transferring files. You can use Notepad++ for editing your code, which makes the process simple and efficient. When it comes to uploading or downloading files, FileZilla is a great tool. It's straightforward and reliable. Next, to connect to our server, Panther, we use PuTTY, which allows us to access the terminal via SSH or Secure Shell. This connection is secure and essential for managing files and running commands remotely. Once connected, if you want to see more details about your files, you can use commands like more to view the file name and contents comprehensively. Now, when it comes to compiling your C programs, you'll use the GCC compiler. The basic syntax is GCC file name output name, but remember, you don't need to include the C extension in the command. Also, adding G includes debug information, which is useful during development. For example, if you're compiling a program called HelloC, you'd type GCC HelloC oh hello G. This creates an executable named hello. Finally, to run your program, you simply type hello in the terminal. This is how you execute your first program and see it in action. This process highlights the essential steps from editing to executing your code, and it ties into the overall theme of working efficiently with remote servers and development environments. Let's take a closer look at how we can print a float value from the rest of the parameter list in our printf statement. In this example, we've got a simple program that calculates the average of 3 values. Notice how we declare our variables, integers for the values and a float for the average. We assign values to value 1, value 2, and value 3, then sum them up. When we compute the average, we divide the sum by 3, but here's the key point. Since sum is an integer and 3 is an integer, the division will perform integer division, which can lead to a loss of precision. To get an accurate floating point average, we need to ensure at least one of the operands is a float. So, we could cast the sum to a float or make 3 a float itself. Now, in our print statement, we use the %f format specifier to print the floating point average. This is important because it tells the program to interpret the variable as a float and display it accordingly. If we used %d here, it would print an integer, which isn't what we want for a fractional value. This example highlights the importance of understanding data types and format specifiers when working with different kinds of variables, especially when mixing integers and floating point numbers. Ultimately, using variables in printf allows for flexible and accurate output, making our programs more informative and professional. Let's talk about variables and identifiers. Variables have names, and we call these names identifiers. An identifier must start with either a letter or an underscore. It's important to remember that C is case sensitive, so uppercase and lowercase letters are treated as different characters. For example, average, average, and average are all considered separate identifiers. Numbers can also appear after the first character of an identifier, but the key point is that the first character cannot be a number. Additionally, C only considers the first 31 characters for external identifiers and the first 63 characters for internal identifiers when distinguishing between different identifiers. This means that if you have longer names, only the first part matters for identification purposes. It's also crucial to know that identifiers cannot be reserved words or special words like int or main. These are reserved by the language and can't be used as variable names. Understanding these rules helps ensure your variable names are valid and meaningful, which makes your code clearer and easier to maintain. Now, let's think about how we can modify our program so it can find the average of any three numbers we choose. The key here is flexibility. Instead of hard-coding specific values, we want the program to work with whatever numbers the user provides. To do that, the first step is to find our three values. We'll ask the user to input each number one by one. Next, we add these values together to get a total sum. Then, we divide this sum by 3 because we're averaging three numbers. Finally, we print out the result so the user can see the average. Remember, the main idea here is to make our program interactive and adaptable, which aligns with our overall goal of creating more versatile and user-friendly programs. Now, let's look at the address of the variable value 1. When we use the scanf function, we're telling the program where to store the input data. The ampersand symbol is crucial here because it indicates the memory address of value 1. This means that when the user types in a number, it will be stored directly in the memory location assigned to value 1. It's important to understand that scanf reads the input as an integer in this case, thanks to the %d format specifier. This process is fundamental because it allows us to gather user input and store it for further calculations. So, in essence, the address of value 1 is where the program will put the number you enter, making it a key part of how data flows into our program. Let's take a closer look at how we're inputting data with scanf. It's important to remember that scanf needs the ampersand symbol before the variable name. This tells the program where to store the input data in memory. Without the ampersand, the program won't know where to put the value, which can lead to errors. Now, moving on to the actual input prompt, we ask the user, "What is the third value?" using printf. This makes the program more interactive and user-friendly. After that, we use scanf to read that third value and store it in the variable value 3. Next, we calculate the sum of the three values, value 1, value 2, and value 3, and store that in the variable sum. Then, we compute the average by dividing the sum by 3. Here, it's important to note that if sum and 3 are both integers, the division will be integer division, which might truncate the decimal part. To get an accurate average, we might need to cast at least one operand to a float. Finally, we display the result with printf, showing the three individual values and their average. This output is formatted to be clear and informative, tying everything together for the user. Throughout this process, we're reinforcing key concepts like proper input handling with scanf, performing calculations, and outputting formatted results, all essential skills in C programming. Connecting these points helps us build a solid foundation for writing effective and reliable code. Let's take a moment to look at how doubles are read on our machine. Essentially, doubles are handled with the LF format specifier, which stands for long float. This means when we're using scanf to input a double, we need to use %lf to tell the program we're expecting a long float value. Now, this is important because it ensures the data is read correctly and stored properly in our variables. Moving on to scanf conversion characters, these are the codes we use within the format string to specify what type of data we're reading. They are crucial for matching the input data type with the variable type we want to store it in. Understanding these conversion characters helps us write more accurate and reliable input code. Overall, mastering these conversion characters, especially for different data types like doubles, is key to effective input handling in C. It ties into our broader goal of writing precise and robust programs that interact smoothly with user input. Now, let's talk about the specifiers %d and %f, which are essential for formatting output in C. These specifiers let us control how numbers are displayed, specifically in terms of spacing and decimal places. The %end format, where n is a number, tells the compiler to use at least n spaces to display an integer in decimal format. This is useful when you want your output to be neatly aligned, especially when printing multiple numbers side by side. On the other hand, the %WNF specifier is used for floating point numbers. Here, W is the minimum width of the display, and n is the number of decimal places. This ensures that your floating point numbers have a consistent number of decimal places, making your output cleaner and easier to read. For example, in our code, we might write printf, the average of %2d, %2d, %2d is %5, 2f\n, value 1, value 2, value 3, average. Notice how the %2d ensures each integer takes up at least 2 spaces, and %5(2f) formats the average with at least 5 characters wide and 2 decimal places. Overall, mastering these format specifiers helps us produce professional, well-aligned output that enhances the clarity of our program's results. Now let's take a closer look at this slide, which focuses on changing the width in formatting. On the left, you'll see some examples of how numbers can be printed with different width specifications. For instance, printing the number 182 with a width of 2 digits using %2d. Then, we see the same number printed with a width of 3 digits with %3d, and so on, increasing the width to 5, 7, and even 9 characters. The idea here is that by adjusting the width, we control how numbers are displayed, especially when aligning output or creating a neat, columnar appearance. Notice how the formatting specifier, like %5d or %7d, ensures that the number occupies at least that many spaces, padding with blanks if necessary. It's also interesting to see how negative numbers are handled with these widths. For example, printing -182 with different widths, you'll see that the negative sign is included within the total width, which can affect the alignment. This concept is crucial when formatting output in programming because it helps us produce clean, readable results. Whether we're printing a list of data, creating tables, or aligning numbers for reports, understanding and controlling width is key. So the main takeaway here is that by changing the width parameter in our format specifiers, we can precisely control how numbers are displayed, making our output more professional and easier to interpret. Now, let's take a closer look at what this slide is really telling us about formatting numbers in print. First, we see the example of printing the number 23 using the format specifier %1d. This tells us that the number should be printed in a field width of 1 character. Since 23 is 2 digits, the output will actually be wider than the specified width, but the key point is that the width indicates the minimum space allocated. Next, we see the same number printed with %2d, which sets the width to 2 characters. Again, because 23 is 2 digits, it fits perfectly here. Then, moving on to %6d, which specifies a width of 6 characters. In this case, the number 23 is right justified in a field of 6, with leading spaces filling the extra space. This pattern continues with %8d and %10d, where the width increases, and we see the number aligned to the right, with spaces padding the left. Notice that in some examples, like -11,023, the negative sign counts as part of the width. For example, with %6d, the negative number will be right justified within 6 characters, including the minus sign. Similarly, for %10d, the number is padded with spaces to occupy 10 characters total, ensuring consistent alignment in columns. These examples highlight the importance of adjusting the width depending on your data and the desired formatting style. By changing the width specifier, we can control how numbers align, especially when printing tables or lists where neatness and readability matter. So, in summary, understanding how to set and modify these widths allows us to format our output precisely, making our data presentation much clearer and more professional. Let's take a closer look at this table, which demonstrates how changing the formatting affects the way our number, 2.7182818828, is printed. First, notice the different format specifiers listed under Formatting. These are instructions we give to our programming language to control how many decimal places or total characters are displayed. For example, with %85f, we're asking for a floating point number with 5 decimal places and a total width of 8 characters. The output is 2.71828, which rounds the number appropriately and aligns it within that width. Next, with %83f, we reduce the decimal places to 3, resulting in 2.718, and again, the total width is maintained. Moving to %82f, it rounds to 2 decimal places, giving us 2.72. When we use %80f, we're asking for no decimal places, and the output rounds to 3, with space padding to keep the width consistent. Now, the more precise formats like %1311f and %1312f show how we can control the number of decimal places very precisely, 11 and 12 decimal digits respectively, while still maintaining a fixed width for alignment purposes. The key takeaway here is that by changing the precision, or the number of decimal places, we can tailor how our data appears, making it more readable or suited to the specific needs of our presentation or analysis. This flexibility is essential when working with numerical data, especially when clarity and precision are both important. So, as we work through different formatting options, remember that adjusting the precision allows us to present numbers exactly how we want, whether that's for simplicity or detailed accuracy. All right, let's take a closer look at this piece of code. Here, we include the standard input-output library with the line include stdio h. This is essential because it allows us to perform input and output operations, like printing to the console or reading user input. Next, we have a comment block that explains what the program does, in this case, calculating the average pay. Comments are really helpful for documenting our code so others, or even ourselves later on, can understand the purpose of different sections. Moving into the main function, which is the entry point of any C program, we see some variable declarations. We have 3 integers, value 1, value 2, and value 3. These are likely going to store individual pay values. Then there are 2 floating point variables, sum and average. These will be used to hold the total of the pay values and the calculated average, respectively. There's also an incomplete line with a string declaration, which seems to be a placeholder or an unfinished statement. This reminds us to always double-check our variable declarations for completeness and correctness. Finally, there's a comment indicating that the next step is to get the first value. Comments like these serve as helpful markers for understanding the flow of the program. Overall, this slide highlights the importance of proper setup in our programs, including headers, clear comments, and thoughtful variable declarations, all of which are foundational for making our code readable and maintainable. So far, all of our programs have used variables to store numbers, not words. But now, let's talk about storing characters or words. We can store one or more characters by writing something like this: char x, sden. Here, x can hold just 1 character, while s can hold up to 9 characters, with 1 space reserved for the null terminator that marks the end of the string. For now, we're focusing on character data mainly for input and output purposes. This means we'll be able to handle individual characters or small words in our programs, which is a key step as we move toward more complex data handling. Remember, understanding how to store and manipulate characters is essential for building more interactive and user-friendly applications. All right, let's take a closer look at this simple yet illustrative program that uses a character variable. What we're seeing here is a basic C program that demonstrates how to handle user input and output using a character array, which is essentially a string in C. First, notice the line include stdio h. This is important because it allows us to use standard input and output functions like printf and scanf. These functions are fundamental for interacting with the user. Inside the main function, we declare a variable called name, which is a character array capable of holding up to 25 characters. This is where we'll store the user's name. Declaring a character array like this is a common way to handle strings in C. Next, we ask the user for their name with printf, which displays the message, "What is your name?" on the screen. Then, we use scanf with the format specifier %s to read the input from the user and store it in the name array. It's important to note that scanf with %s reads input until it encounters whitespace, so it works well for single-word names. Finally, we greet the user by name with another printf statement, inserting the name variable into the message using %s. This creates a personalized response, which makes the program more interactive and friendly. The key takeaway here is how we use a character variable, or more precisely, a character array, to store and manipulate text input from the user. This is a foundational concept in C programming, especially when we're working with strings. It connects to our overall theme of understanding data types and how they enable us to write more dynamic programs. So, in summary, this example illustrates how to declare a character array, use printf and scanf for user interaction, and incorporate user input into output. It's a straightforward but powerful demonstration of handling textual data in C. Now, let's talk about including different variable types in our C programs. You have int, float, and char. These are the basic data types you'll use to store different kinds of information. When reading input from the user, you use scanf, but remember, you need to include an ampersand and before the variable name. This is because scanf requires the address of the variable to store the input correctly. Next, when it comes to printing output, printf is your go-to function. To format your output properly, you use format strings like %f for floats, %d for integers, %u for unsigned integers, %c for characters, and %s for strings or character arrays. Finally, to make your code clearer, you can add comments using / or to explain sections or specific lines. These comments are really helpful for understanding your code later on or when sharing with others. So, overall, understanding how to read different variable types and print them with the correct format strings is fundamental in C programming, and proper commenting makes your code more readable and maintainable. Let's take a closer look at this structure. When we use an if statement, we're essentially checking a Boolean expression, and if that condition is true, the statements inside the block will execute. Now, what happens if that condition isn't true? That's where the else if comes in. We can have multiple else ifs, each checking a different Boolean expression. If one of those evaluates to true, its corresponding statements will run. And if none of the if or else if conditions are true, we have the final else block. This acts as a catch-all, executing if all previous conditions have failed. Understanding these control flow statements, if, and else, is crucial because they allow us to handle different scenarios in our programs. They help us make decisions and execute different blocks of code based on specific conditions, which is fundamental to creating dynamic and responsive applications. Remember, using these structures effectively means carefully planning your Boolean expressions to cover all relevant cases, ensuring your program behaves as expected in various situations. Let's take a closer look at this simple C program, isItNegC, which is designed to illustrate how we can determine if a number is negative or not. First, we include the standard input-output library with include stdio h, which allows us to use functions like printf and scanf. Moving into the main function, we declare a variable called number of type float, so we can handle decimal values. The program then prompts the user with printf to enter a number, asking, "Please enter a number." After that, it uses scanf to read the user's input and store it in our number variable. Now, the core logic hinges on an if statement that checks whether the number is less than 0. If it is, the program prints out that this number is a negative number, using printf to display the value along with the message. If the number isn't less than 0, meaning it's 0 or positive, the else branch executes, and the program informs the user that the number is not negative. This simple example demonstrates how conditional statements work in C to make decisions based on user input. It highlights the importance of understanding control flow, which is fundamental to programming. As part of our overall theme, it shows how we can create interactive programs that respond differently depending on the data provided by the user. Now, let's take a closer look at relational operators. These are fundamental in programming because they allow us to compare values and make decisions based on those comparisons. On this slide, we see a table that summarizes the most common relational operators and their meanings. First up, we have the double equals sign, which is used to check if two values are equal. For example, x equals y. It's important to remember that in most programming languages, a single equals sign is used for assignment, so to compare for equality, we need to use double equals. Next is the not equal to operator, written as equals. This checks if two values are different, like 1 equals 0, which would evaluate to true because 1 is not equal to 0. Moving on, we have the greater than operator, represented by. This is used when we want to see if one value exceeds another, such as x plus 1y. Similarly, the less than operator checks if one value is smaller than another, for example, x12x. Then, we have the greater than or equal to operator, greater or equal. This tests whether a value is either greater than or exactly equal to another, like +1 greater or equals 0. And finally, the less than or equal to operator determines if a value is less than or equal to another, such as x plus 7 less or equal 10. These relational operators are key tools for controlling the flow of your program. They enable you to create conditions and make decisions, which is at the heart of programming logic. Remember, mastering these operators is essential for writing effective and efficient code that can respond dynamically to different situations. So, in our current compound interest program, we're printing out the values for every year. But, printing every single year can be a bit overwhelming and not always necessary. Often, looking at just every 10 or 20 years gives us a good overview. What we really want to do, though, is to focus on specific years, specifically those that end in a 5. So, for example, the year 5, 15, 25, and so on. These are the years where the remainder when divided by 10 is 5. This is where the concept of integer division comes into play. It helps us determine if the year ends in 5 by checking the remainder when dividing by 10. If that remainder is 5, then we know that year ends in a 5. This approach makes our output much more targeted and relevant, especially when we're interested in key points in time rather than every single year. It connects nicely with our overall goal of making the data more manageable and meaningful. Let's take a closer look at these results. What we're seeing here are various examples of integer division and the corresponding modulus, or remainder, results. Notice that for positive numbers like 8 divided by 3, the quotient is 2, and the remainder is 2. That's pretty straightforward. But things get interesting when we look at negative numbers, such as -8 divided by 3. The quotient is -2, but the remainder is -2. This might seem unusual if you're used to the typical definition of remainders being positive, but it highlights how programming languages can handle division differently. Similarly, when dividing 49 by 7, the quotient is 7, and the remainder is 0, indicating 49 is divisible evenly by 7. Now look at divided by 3. The quotient is -16, but the remainder is. This shows that the sign of the remainder depends on the dividend and divisor, and that the remainder can be negative, which is important to understand for accurate calculations. Overall, these examples demonstrate that integer division and modulus operations can behave differently depending on whether the numbers are positive or negative, and understanding this helps us write correct and predictable code. Now, let's take a look at how sizes are implemented depending on limits h. For the int data type, the range is from up to 2,147,480,3,647. Moving on to short, it covers from minus 32,768 to 32,767. For long, the range is much larger, spanning from to 9,223,372,854,775,807. When it comes to floating point numbers, the float type can represent values roughly from 1.17 times 10 to the power of minus 38 up to about 3.4 times 10 to the power of 38. And a quick note on unsigned types. The keyword unsigned starts at 0 and can go higher, effectively doubling the positive range for the same size. When choosing data types, it's important to consider these sizes and ranges carefully. Picking the right type ensures your program uses memory efficiently and avoids overflow errors. This ties into our overall theme of understanding data types to write more reliable and optimized code. Now, let's explore the two ways of defining constants in C first. There's define, which acts as a preprocessor directive. What this means is that before the actual compilation begins, the preprocessor replaces every occurrence of the constant's name with its value. It's a simple and widely used method. The general form looks like this. Define, followed by the constant name, then the constant value. For example, you might see define with holding rate 0.8 or define prompt y. Other examples include define answer, yes, define maxpeople 15, hash define inchperf 12, and define speed limit 55. The key takeaway here is that hash define is a straightforward way to create constants that can be used throughout your code, making it more readable and easier to manage. This approach ties into our overall theme of writing clear, maintainable code by using constants effectively. All right, let's take a closer look at the general form of declaring constants in C++. Basically, we start with the keyword const, followed by the data type, then the name of the constant, and finally the value assigned to it. You can see that in the example, const float with holding rate equals 0.8. It's important to note that constants can also be declared with multiple names in a single statement, separated by commas. For example, const char prompt equals y, answer equals yes. Here, prompt is a character, and answer is an array of characters or a string. Similarly, you can declare multiple integer constants together, like maxpeople equals 15, inchperf equals 12, and even speed limit equals 55, all in one go. This approach makes your code cleaner and easier to manage. Remember, declaring constants is a great way to make your code more readable and maintainable, especially when you have values that shouldn't change throughout your program. It helps prevent accidental modifications and makes your intentions clear to anyone reading your code. Let's now compare some fundamental features of C and Java to understand their differences and strengths. First, the nature of the languages. C is a function-oriented or imperative language, meaning it focuses on procedures and commands to perform tasks. Java, on the other hand, is object-oriented, emphasizing objects and classes as the core building blocks. When it comes to file naming conventions, C typically uses extensions like C and H, such as stackc and stacch, with the file name often matching the data structure or module. Java, however, uses a single file named after the class, like stackjava, which helps keep the code organized and intuitive. The basic programming units differ as well. In C, we primarily work with functions. These are the fundamental units of code execution. Java relies on classes and abstract data types, which encapsulate data and behavior together, supporting the object-oriented approach. Portability of source code is possible in both languages if we follow good discipline. However, when it comes to compiled code, C is less portable. Code must be recompiled for each architecture. Java shines here with its write once, run anywhere philosophy, thanks to its bytecode, which can run on any system with a Java virtual machine. Speaking of compilation, C code is compiled with GCC, converting it into machine language specific to the target architecture. Java uses the JAVAC compiler to produce bytecode, which is executed by the Java virtual machine, making it platform independent. Buffer overflows are a common concern in C. They can lead to segmentation faults, code dumps, and unpredictable behavior if not carefully managed. Java, however, performs runtime checks, and such errors throw exceptions, making programs more stable and secure. For Boolean types, C uses an int, 0 for false and non-zero for true, or includes stdbool, H to use a dedicated bool type. Java has its own Boolean type, which explicitly stores true or false, making code clearer and less error-prone. Regarding character types, C's char is typically 8 bits, representing ASCII characters. Java's char is 16 bits, supporting Unicode, which allows for internationalization and a broader set of characters. When it comes to strings, C uses null-terminated character arrays, which can be tricky to manage. Java offers a built-in, immutable string data type that simplifies string handling and manipulation. Finally, accessing libraries differs as well. In C, we include headers like include stdio, h. In Java, we import packages such as java.io, file to access library functions. Overall, these differences highlight how Java's design emphasizes portability, safety, and ease of use, while C offers more control and efficiency, but requires more careful management. Understanding these distinctions helps us choose the right language for each task and leverage their strengths effectively. Let's take a look at some key differences between C and Java, starting with how they handle printing to standard output. In C, you use print with format specifiers like printf, sum equals %d, x. In Java, you typically use system, out, println concatenating strings and variables, so you'd write system, out, println, sum plus. For formatted printing, C uses print with specific format specifiers such as printf, avg equals %32f, avg, while Java offers system, out, printf, which works similarly. Next, reading from standard input, C uses scanf with format specifiers, scanf, %d, and x, whereas Java has more straightforward methods like int x equals stdin, read int, which makes input handling cleaner. When it comes to declaring constants, C uses define or const, but Java uses the final keyword. This makes constants more type-safe and integrated into the language. For loops are quite similar in syntax, both using the for statement, like for I equals 0, in, I++. However, Java encourages declaring the loop variable within the for statement itself, as in for int I equals 0, in, I++. Variable auto-initialization is another difference. In C, it's not guaranteed. Variables can have indeterminate values unless explicitly initialized. In Java, instance variables, including array elements, are automatically initialized to default values like 0, null, or false, which helps prevent bugs. Casting in C is very flexible. You can cast anything to anything. Java's casting is more controlled. It may throw checked exceptions at runtime or compile time if the cast is invalid, promoting safer code. Regarding demotions, C performs automatic casting but might lose precision, like when converting from double to int. Java requires you to do this explicitly, for example, casting a long to an int with int, making the programmer responsible for potential data loss. Variable declaration rules differ too. In C, you typically declare your variables at the beginning of a block, whereas in Java, you can declare them just before you use them, which can make code more readable and flexible. Finally, nomming conventions differ. C often uses underscores, like sum of squares, while Java prefers camel case, such as sum of squares, aligning with its style guidelines. Overall, these differences highlight Java's emphasis on safety, clarity, and modern programming practices compared to C. All right, on this slide, I want to walk you through some of the essential tools we'll be using throughout our project. First up is Notepad++, which is a really powerful text editor that makes coding easier with features like syntax highlighting and multiple file editing. Next, we have FileZilla, which is a popular FTP client that allows us to transfer files quickly and securely between our local machine and remote servers. Then there's Panther, which is part of the GCC toolchain, and it's used for compiling and managing our C or C++ code. PuTTY is another important tool. It's a terminal emulator that helps us connect to remote servers via SSH, making remote management straightforward. Understanding our program's file structure is also crucial. We'll organize our code files properly, typically using include statements like #include for system or library headers and include for our own project files. The main function is the entry point of any C or C++ program. It's where execution begins, and understanding its structure is key to writing effective code. Finally, I want to emphasize that these tools and concepts all connect to the bigger picture: writing, managing, and debugging our code efficiently, which is fundamental to the overall success of our project. Now let's talk about variables. In C programming, we have different types such as int, float, and char. Each of these serves a specific purpose. For example, int is used for integers, float for decimal numbers, and char for single characters. We also have the unsigned keyword, which is used to declare variables that can only hold non-negative values, effectively doubling the upper limit of the variable's range. When working with strings, we typically define them as character arrays. For instance, you might see something like char name26, which allocates space for a string of up to 25 characters plus the null terminator. For Booleans, C doesn't have a built-in bool type by default, so we include the stdbool header file, which defines the bool type and the values true and false. Moving on to constants, we have two main ways to define them. The first is with the define directive, like define name value, which creates a macro. The second is using the const keyword, such as const type name equals, which creates a variable whose value cannot change during program execution. To get the address of a variable, we use an operator. This is useful for pointers and memory management. And if we need to convert or interpret data types, we use casting, like type var, to explicitly convert a variable to a different type. In summary, understanding these fundamental elements, variable types, string definitions, constants, pointers, and casting, is crucial because they form the core building blocks of any C program and help us write more efficient and effective code. All right, let's wrap things up by reviewing some key functions and concepts. When working with input and output in C, we use functions like scanf and printf. Remember, scanf reads from the screen and requires a control string along with the addresses of variables where the input will be stored. On the other hand, printf is used to display information, inserting variables into a string at specified locations. Now, speaking of format strings, we have several important placeholders. For example, %2f for floating point numbers, %d for integers, %s for strings, and %u for unsigned integers. These format specifiers help us control how data appears on the screen, making our programs more flexible and user-friendly. Moving on, we also touched on decision-making with if, and else statements. These are crucial for controlling the flow of our programs based on certain conditions. They allow us to execute different blocks of code depending on the situation, which is fundamental to creating dynamic and responsive programs. And that brings us to the summary of the entire presentation. We've covered the core concepts of input-output functions, format strings, and decision-making structures. Understanding these building blocks is essential for writing effective C programs. Thanks for your attention, and I hope you now feel more confident in applying these basics to your coding projects.